Happy learning! Today we're going to talk about trees. Okay, so in previous sections, if you've been following along with this series, you would notice that most of the examples that we've looked at so far have involved finding routes on a graph, either visiting every edge or visiting every vertex or going from one vertex to another as quickly as possible. So in previous sections, we focused on finding routes within a graph. So today we're going to look at a slightly different type of question that is not going to be able to be solved using finding a route in a graph. Okay? So imagine you have this scenario where you have some employees in an office. So these are like the employees' desks, and maybe they have some sensitive information. So we don't want to be using Wi-Fi because that could be compromised. And so we're going to hardwire their computers to some central server. Okay, and so the question is, how do we lay down the wiring to make it as cheap as possible? Okay, so we could do something like this. Right? This would be pretty efficient. If we added another wire here, that's not necessary, right? We just need our computers to be attached to the central server. Or maybe we have something like this. This might actually be a little bit better. It's tough. I don't know what the geometry is of our graph. We don't have weights drawn on. But this is another way where we're not using extra wire just for the sake of using it. Okay? So we're just concerned, our main concern is that all locations or vertices are connected. Okay, that's what we're interested in today. And this type of graph is going to be called a tree, because when we start looking at trees, they do kind of look like trees. All right, so let's define what a tree is. A graph G is called acyclic. What does it mean for a graph to be acyclic? It means that there are no cycles. Or circuits. All right, so this graph, you can't find a cycle or a circuit on it. So this is certainly acyclic. A graph G is a network if it is connected. Okay, so a connected graph, another way to say that is it's a network. Okay, and so we're finally ready to define what a tree is. A graph G is a tree if it is an acyclic network. So this here is a tree. Okay, go to your biology professor and show them this graph and say, that's a tree. I'm not sure what you're talking about. Okay, so if there's no cycles, and it's connected, we got ourselves a tree. And we're going to be interested in finding trees that connect all the vertices as cheaply as possible. Okay. What if we had a bunch of trees? What would that be called? So let me know in the comments what you would call a bunch of trees. Okay, I hope you gave an answer. A forest is a collection of trees. So a graph G is a forest if it is an acyclic disconnected graph. Okay, so each of the components of the graph would be a tree, and then the whole thing is a forest. One last definition. A vertex, so this is not continuing here. So a vertex of degree 1 is a leaf. Okay, so in this tree here, that's a leaf, that's a leaf, that's a leaf. These are not leaves. All right, so let me just give you an example of what trees could look like. All right, so for example, maybe you have something like this. Right, you're starting to see this tree shape. Okay, and then another example that you see in the real world is the family tree. Okay, so the family tree is you have a bunch of grandparents. They have kids. Maybe they have a bunch of kids. Let's just say, for purposes, they only have one kid. And it's your mom and your dad, and they have kids, and it's you. Okay, so this is a family tree. If you get high enough, unfortunately, if you get high enough, if you go enough generations back, it's not a tree anymore, because there's probably going to be some parts that go like this, where we get a cycle. Okay, so locally, you know, if you go back a few generations, it's a tree, but if you go back enough generations, it's no longer a tree. So trees have applications to probability. They have applications to chemistry. They have applications to computer science. So these are like a very important mathematical object. But today we're just really going to talk about the basics. Okay, so this might be a little bit of a shorter video, but hey, who's complaining? So what I want to do now is just state some properties about trees. These properties are going to play a big role when we actually go to find trees lying inside of a graph. Okay, so these are some properties of trees. Okay, first property. For every n greater than 1, any tree with n vertices has n minus 1 edges. Okay, so you can see here, this tree has 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices, and 1, 2, 3, 4, 5, 6, 7, 8 edges. 9 vertices, 8 edges. This tree has 7 vertices and 1, 2, 3, 4, 5, 6 edges. So if you're a tree and you have n vertices, you're going to have n minus 1 edges. Okay, but now ask yourself, is it possible for a graph to have n minus 1 edges and not be a tree? Okay, so think about that. A hint should be it's probably possible, or else I would have said if and only if, you know. So think about how that is, and let me know in the comments if you're able to think of an example. Okay, so 2, for any tree with, again, n greater than or equal to 1 vertices, the sum of the degrees is 2n minus 2. Okay, so just if you remember back a few videos ago, we had the handshake lemma that said the sum of the degrees is twice the number of edges. Okay, so the sum of the degrees is 2 times n minus 1, which is this. All right, so if you're a handshake lemma enjoyer, this number 2 should have been obvious to you. Okay, every tree contains at least 2 leaves. Unless the tree is a single vertex. Okay, so if your tree is just like this, if that's your whole graph and it's just a single vertex, okay, of course there's not 2 vertices that are leaves, but any other tree has at least 2 leaves. Here we have a bunch of leaves, right? 1, 2, 3, 4, 5 leaves. And here we have 1, 2, 3, 4 leaves. Okay, that's at least 2. Okay, this next property kind of ties into this first one. Any network. Okay, so a network is a connected graph. Any connected graph on n vertices with n minus 1 edges must be a tree. Okay, so if it's connected and has n minus 1 edges, it must be a tree. Okay, so it's almost saying the converse of this, but not quite. So we need it to be connected. Okay, just a few more. Number 5 says, for any 2 vertices in a tree, there is a unique path between them. Okay, I know I just erased this tree, but let's draw a tree again. So let's say we're trying to find the path between this vertex and this vertex. There is a unique one. You have to go down this way and around and back up. Okay, and you can check for any pair of vertices on a tree. There is a unique path between them. Remember, a path means we're not repeating any vertices. And 6, the removal of any edge of a tree disconnects the graph. Okay, so if you take any of these edges out, we're going to be left with a disconnected graph. So if we, remember, our goal eventually will be to have all the vertices connected. So we're going to want to get a tree. And then we can't do any smaller than a tree because we'll be left with a disconnected graph. Okay, well, that's all I have for today. Sorry that the video is a little bit shorter. If you're looking for more, if you're looking for a longer video, just start the video over and watch it again. Okay, so let me know in the comments if you have any questions. Let me know if you have any thoughts about trees. And then, yeah, in the next video, we're going to talk about finding these spanning trees. Okay, see you later. Bye-bye.